Okay, you want me to take it away now?
Yeah.
Well, let me introduce you just for a
Yeah.
second. This is Rich Benz, and I got in touch with Dr. Feiger because I know him as Don or Donnie Feiger. He was a student of mine well, a long time ago, um, and one of the things that just a couple little stories about Dr. Feiger and or Don to kind of introduce
Hi. There they are. Come in, come in. Thank you.
my interaction with him. Uh, Back when he was a student, I was teaching, of course, biology, and at Wycliffe High School. Don was not in my biology class, but I believe he was in my science research class. Uh, but the biggest interaction that I had with Don is that I would interact. Well, the first one was his older brother came to me when I was teaching photography and asked if I would help his little brother, who was still at junior high, to learn how to develop some infrared film. And I was impressed that, first of all, that one of my students knew what infrared film was, and that two, he had a little brother that wanted to develop it. So that was my first introduction to Don. Then when he got up to the high school, the biggest influence I had, I think, is when he would come into school late, to come into school tardy, because he was up all night on his garage roof with his telescope, uh, doing research or at least observing variable stars. I would kind of intervene between the main office and Don to kind of get him off the hook and to tell Don, you got to come in with a note at least. Then the next interaction was when he was in my class, and I kind of taught him about writing proposals for funding, just the introduction, and he's gone way beyond what I've ever known or done with that. And you can look at his bios to see that. And then finally, when he was a senior and he was doing research on variable stars, he had developed an instrument and an algorithm to measure light intensities, I believe, and he could tell you the specifics. He got an award at one of the state science competitions, and while he was there, a research astronomer had been one of the judges and really liked what he was doing and invited him out to his place out west, I believe in Colorado, to observe some of the variable stars. And Don went out, and he went out by himself. I mean, that was his mom came to me and she said, "Is this guy legit?" And I said, "I don't know. I think he is." So they had this adventure going out there, and unfortunately, it was during the time when there was a full moon. And I always scratched my head thinking, two big astronomers ought to know when the full moon is. Now, I've kind of enhanced that story a little bit, but I always had fun telling it. One of the things that I've been amazed with Don Feiger as he's gone through his education and his career are the big influences that he's had. He did his research and he discovered the Pistol Star cluster. He worked with helping to schedule the Hubble telescope, and then eventually he was brought to Rochester Institute of Technology to head a new institute that they were starting. And you can read his biography to get the details of that. But as you could see, I've been amazed and extremely proud that Don Feiger has done what he's done, and I think it's time to hear from him now.
Okay, great. Thank you, Mr. Benz. And I remember most of that. So I'm very happy that I'm not so old that I've forgotten it all.
Right.
And I think it was pretty accurate. So I'm going to go ahead and give this talk. Mr. Benz asked me to give a talk, and I thought the James Webb Space Telescope was an interesting and timely topic to discuss. I imagine most of you have probably heard about it. And so, what I'm going to do is tell you about the development of the Space Telescope and then some early results. And I thought to start us off, I would ask ChatGPT to write us a haiku. So it says, James Webb's keen eye, unveiling cosmic secrets, galaxies unfold. I think it did a pretty good job. I like that one. Now, what I'm going to do next is show you a video, and I'm hoping that there's audio. If not, it's okay. Just tell me if you hear the audio. You would have to probably turn it up quite a bit. Maybe some of you recognize this song. Some of the younger people do not. But this is the James Webb Space Telescope unfolding in space.
2001, yeah.
Yeah, the telescope was so big, we couldn't launch it, expand it out. We had to crunch it up. And so you can see those yellow hexagonal mirrors. What you're looking at is pure gold. So those are gold plated. And then these mylar sheets block the sunlight because the sunlight's bad. We don't want sunlight in the telescope. And you can see the multi-layer insulation extending. At this point, you might realize a lot of things can go wrong when this thing unfolds in space. Like those sun blockers could have gotten crinkled. And there's the secondary mirror on the boom. And then there's the primary mirror that's fully formed now. Again, we couldn't launch one full mirror because it wouldn't fit in the rocket. There was no rocket big enough. Now, usually the students know this next song, but the parents don't. So it's sort of the opposite. And now finally I can show these results. So these are all images from the James Webb Space Telescope. And before, a few years ago, I couldn't show this. I had to just show the beginning animation. So I'm going to talk about some of these results in a little bit. But first of all, let me backtrack a little bit and tell you about myself. I'm a professor at RIT in the College of Science, and I have appointments in various programs. One is the Astrophysical Sciences and Technology PhD program at RIT. I'm director of the Center for Detectors. We develop detectors for a broad range of applications, including astrophysics. We have 8 professors and 65 people total in 5 different colleges. And I'm also director of the Future Photon Initiative at RIT, which brings together the collection of people at RIT who use photons for something. So they use light for some reason. Either they make light, or they detect light, or manipulate light, or use light for quantum photonics, or they develop material system from which we can make light devices, etc. So everything about light. I came here in 2006, and previously I was at the Space Telescope Science Institute, which at the time operated Hubble and now operates both Hubble and the James Webb Space Telescope. There's a picture of it there, and it's on the Homewood campus of the Johns Hopkins University. And there's a picture of Hubble and a picture of JWST. And before that, I was at UCLA in an infrared lab designing optics for an infrared spectrograph in the world's largest telescope, the Keck telescope. That instrument was used to gather data that eventually won the Nobel Prize in 2020 by the UCLA group. I wasn't there at the time, but I was there developing the spectrograph that was used for the Nobel Prize. There's a picture of the twin Keck domes with the world's largest telescope in them. So I'm interested in detectors, and there's a little detector. You can see the purple glove holding a detector, and massive star clusters, massive stars, and the galactic center. That's what you're seeing in those pictures in the bottom right. I have three daughters. I don't have pets, and I have a few plants, and I'm happy to report most of them are alive. So here's a snapshot of my career trajectory. By the way, it's interesting in my field that when people give professional talks, they're now asked to present this information. And I think it's because we want to tell students how we got where we are. So my story, I guess, starts around 8 years old. Decided to be an astronomer. I remember I had a book of jobs. It was I forget what it was called, like the field guide of jobs or something or other. Every page was a different job, and there was a page for astronomer, and I was excited by this. And I went to my mother and I showed her the page, and there's a little field at the bottom that says competitiveness, and next to it, it had the word keen. And so I told my mom I was really keen to be an astronomer, and she said, "No, no, no, that means it's difficult." And so I said, "Okay, well, I guess I got to work hard." So that set me off on working very hard. Uh, my uncle was an important influence in my early life. He was the only quote unquote intellectual. Everyone else worked at the same factory, Lincoln Electric, which you probably know about. I'm the black sheep of the family. I didn't work at Lincoln Electric. Instead, I went to college. And my uncle would talk to me about philosophy and religion and the universe. Now, in parentheses, by the way, I have my age there. And at one point, I was doing photographic photometry, and my mother, I think, contacted Case, and she did this now and then. She would make connections for me, so I learned a lot from my mother about that, about how to make connections with people. And I met a professor, William P. Beidelman, and he had a big cabinet full of note cards, and each note card had all these notes about each star, peculiar variable stars. And he let me use his microdensitometer. I don't know if that's what I'm looking at in this picture, but it's a way to look at photographic film and measure the sizes of stars and therefore estimate their brightnesses. So it's a brightness estimating tool. And this was important to me because I ended up wanting to study variable stars, probably initially just because they change brightness and it gets boring looking at stars that don't do anything. So I started out with photographic photometry, then I did visual photometry, which means I didn't use a camera or film. I just used my eyes to measure the brightnesses of stars. And then I got lucky. I wrote a proposal, I think with Mr. Benz's help, to the Ohio Academy of Sciences. And Lynn Elfner, who I know Mr. Benz knows, and maybe some of you have heard him, he was in charge of this grant program. And I wanted to buy a widget that would measure the brightness electronically of a star, and I would take the widget and put it on a telescope. That was the idea. I don't know if it was if I was supposed to write a proposal because I was a high school student, and I can't remember if that grant program was for real scientists or high school students. So it turns out this fellow, Lynn Alfner, was a aficionado of photoelectric photometry. So of all the things in the world, the guy in charge of the grant program was a photoelectric photometrist. So I got lucky there and I got funding. And by the way, I got funding from a lot of other places too, like a Bailey Meter would fund my trips to science competitions. I'd go with Mr. Benz. And Lubrizol gave me funding. And so it's kind of nice that the community gives funding to support these kinds of things. So here's me in I think it's the News Herald or something, and you can see my telescope, and at the bottom of the telescope you can see the photoelectric photometer. All my friends ask me why I took a picture with a garbage can, but it's not a garbage can. It's a telescope, and I still have that telescope in my garage. And here I am at some sort of science competition, I think, and there's Mr. Benz who came along on many of those trips. I ended up writing some software for the photoelectric photometry and then sold the software back to the company who made the photometer, and they sold the software to other people. I pursued astronomical observation and instrumentation in college. I went to Northwestern, and for my thesis, I discovered hot young stars in the galactic center. I discovered the Pistol Star. I discovered the Arches cluster, which is the most massive young cluster in the galaxy. And I tried to convince my daughters that the hairstyle in that picture was very much in fashion at the time. I don't think they believed me. And there I am at the Lick 3-meter Shane telescope, just outside of San Jose, which is what I use now. 96% of astronomy PhDs fail to get a faculty position. So 100% want a faculty position. 96% don't. So what they tell students is have some off ramps so you can do something for a living. And so I pursued optical engineering, and I also interviewed at the most successful hedge fund in the world. I made it a few rounds into the interviews until at the end they told me that they were only hiring Russian field medalists. And so I politely told them it would have been good to know that at the beginning, because that is not me. But those are the smartest mathematicians in the world. Met lots of people in the field, which is a real pleasure. That's one of the side effects of being an astrophysicist. I have a permanent job now, so I can wear my Elvis outfit and they can't fire me. I wear that every Halloween for my students. So why build the James Webb Space Telescope? So the project is motivated by a desire to untangle the quote unquote cosmic web of the early universe. And I'll show you what I mean by that. One of the goals was to see the first galaxies that formed after the Big Bang, see the first stars, the first generation of stars, probe star formation, which is generally hidden from our sight because it's usually surrounded by a dust cocoon. We can't see into it unless we use infrared. Characterize exoplanets. That's the word used for planets outside of our solar system. And when I was a student, we didn't have exoplanets. And we also walked uphill in 2 feet of snow every day to school. That's what I tell my daughters. We didn't have exoplanets. Now there are thousands. And I used to eat lunch with the guys who discovered them. And it was funny because at the time, exoplanets wasn't really a topic. Real astronomers didn't try to find exoplanets. And these guys basically couldn't get jobs. They barely had jobs. And so I'd see them at the telescope and after a night of observing, looking for exoplanets. So the James Webb Space Telescope was meant to characterize or measure the properties of exoplanets. So what all this means is if you take the 5 first bullets, it means that you need a big, cooled space telescope with infrared detectors. So in this slide, you see the process of stating high-level science goals and then extrapolating from those what kind of device we need. So I started on this project in 1999 with a small team of a few dozen people, scientists and engineers at Space Telescope Science Institute and NASA. And at the time, we were saying we would launch in 2007 for $600 million. So every year I would show my class a graphic, and I had to keep updating it. The launch slipped a little bit. So we launched on Christmas Day 2021. So we were a day late and $1 short. It turned out to be about $11 billion, not 600 million. So we're off by a factor of 20, I guess. It was NASA's riskiest mission. It had the most single point failures on it, over 200 single point failures. That means if one of those things didn't work, the whole mission wouldn't work. And many of us were very surprised when the thing worked, and it does work. So let me tell you what I mean by cosmic web. You can see the graphic on the right. It looks a bit peculiar. There's a circle in the outer part, and then it looks like a couple pie slices of somewhat randomly located colored dots. But if you look at that, the colored dots are not randomly located. It looks like they're preferentially distributed in these linear strands. And it kind of looks like a web. And so we call this the cosmic web. Each of those dots represents a galaxy. Each galaxy is a few hundred billion stars. And at the center is us. And so someone went out and detected all these galaxies, measured their distances and their location and angle around us, and made this plot. And it appears that galaxies are distributed not randomly, but it's instead they're arranged in this kind of cosmic web. And one way to think about this is imagine having a handful of soap, and you can blow air into the soap bubbles, and the soap bubbles expand, and the bubbles touch each other on their edges. Well, the matter in a soap bubble is at the edges. That's where the matter is. Inside the bubble is just air. And so what we think is happening here is that uh, there were quote unquote these bubbles in the early universe that expanded, and the galaxies formed on the edges of the bubbles. And we call this the cosmic web. So this is one of the things we wanted to figure out with the James Webb Space Telescope. I've already said these words, so I'm just going to move on. So this is another graphic that we like to show people, and it's good for the background. It's maybe a bit confusing. This graphic represents the whole history of the universe. On the left, you see that bright light, the white light. That's the Big Bang, and it's the beginning of the universe. And then on the right, after 13.7 billion years, that's where we exist. And so as we look out in the universe, we can see objects that are very far away, and we're seeing them as they existed many years ago. So for instance, I don't know if you can see my cursor here, but I'll move it around anyway. You can see this location here called the first stars. We believe the first stars formed a few 100 million years ago. And if we can see light from them, we're seeing them as they existed about 13.5 billion years ago. So the further we look, the longer it took the light to get to us. So that means that we're looking at objects as they existed a long time ago. So one of the things we used to say is the James Webb Space Telescope is a cosmic time machine. So you can see in this picture in the early days during the Big Bang, nothing much existed except pure energy, which turned into gluons, quarks, and then subatomic particles, and eventually atoms. And there was a point where the atoms, the electrons recombined with the atoms, and then photons could travel out unimpeded. And we see those photons now. So we see photons that were emitted by the universe only a few 100,000 years after the Big Bang. I know a few 100,000 years sounds like a lot, but not compared to 13.7 billion. So we can see photons from this period 400,000 years ago, and we call that the cosmic microwave background. Maybe you've heard that before. So we're looking at the imprint of these fluctuations in the universe at the time that the atoms recombined. So the James Webb Space Telescope was built so we could find the first stars and the first galaxies. So we want to see objects a few 100 million years after the Big Bang. And we want to do that because we have predictions about how quickly stars and galaxies should have formed after the Big Bang. And in science, we make predictions and then we make measurements. And that's what the James Webb Space Telescope is doing now. So why use a big telescope? So the collecting power of a telescope is related to its size, the size of the mirror. The bigger the mirror, the more light it collects. And the more light it collects, the fainter the objects it can see. So we need to be able to see fainter things that we haven't been able to see before. So we need a big telescope. There's also something else which is peculiar, and it is a result of some basic optical physics, and that is the ability to separate objects that are close together scales with the size of a telescope. A bigger telescope has better spatial resolution, so you can see objects that are closer to each other. So if you want to see galaxies that are next to each other in the early universe, and there's a high density distribution of them, you'd want to have a higher resolution telescope. So again, this simply says, the second bullet says, yes, we need a big telescope for that reason also. So we always want bigger telescopes. And here's a little digression about the physics. Some of you might know this, but it turns out if you build an optical system and try to image a point-like object in space, maybe it's kind of like an LED or something that emits light, the image that's formed is not a point. So this is unfortunate. It turns out due to something called diffraction, the point actually is a blur. And this surface plot is something I made with a computer program. It's the image of what a dot of light would look like as made by an optical system. And hopefully you can look at that and realize that's not a dot. Instead, it has a certain width to it, and it also has these ripples. And you can't get away from this. This is a basic artifact of physics. So it's kind of like
Hello?
a central. Yes.
Wonder if I could ask you a question about your other slide where you were showing the history, and you mentioned the Earth. I thought you said was on the far right-hand side. Was that correct?
Yeah. So we in our galaxy are sitting at the present time, which corresponds to the rightmost point shown by this line and arrow in the bottom right.
Okay, my question would be then, if you turned the telescope further to the right, I assume there is no light there. Is that correct?
Yeah, it's the future. It hasn't happened yet.
Okay, so that has been done. The telescope has been turned in the direction of the right of that slide.
Well, the direction horizontally in right left is time. So we can't see the future. If you came back to this talk a billion years from now, we could extend this plot a little bit to the right by a billion years, but we'd have to wait for the billion years. We can't see in the future.
Okay. Thank you.
Yes, yes, good question. We've got this problem, this blur, and I won't read all these words. Some of this is from my lectures, but I've said many of these words already. But basically, look at this picture on the right. What that's meant to represent is the images of two stars, and instead of being dots, points, they're blurs. And two stars that are close together will look like two blended blurs. And so at some point, as the stars get closer, we can no longer tell that there are two stars. I think the distance that you see between these two stars, this is a simulation, but this distance is probably the minimum before the two stars blend so much that you can't even tell that there are two stars. And this minimum angle is called the Rayleigh criterion. And these again are simulations of the blur. Remember the central blur with the rings around it? That's what the pattern looks like that an optical system makes for a point-like object. At the bottom are two stars simulated that are near each other. And basically, this is all I wanted to tell you. Look at the equation at the very bottom. There's a capital D in the denominator. And all that means is as the telescope gets bigger, we can see objects that are closer together. That's it. That's the whole point. So we want a big JWST so it can gather a bunch of light and see fine detail. That's what this says. It's hard to make big mirrors. It's really hard to make big mirrors and launch them in space because we don't have rockets big enough. So someone had to pioneer the technology of making a big mirror by taking small segments and putting them together. And that's what you can see here. These are the Keck telescopes in Hawaii. On the right, you can see a fellow with a red jumpsuit. He's sitting in the hole in the middle of the mirror. And this kind of segmentation is what we used on the James Webb Space Telescope. You saw in the video I showed you at the beginning the gold segmented mirrors unfolding and creating one big mirror. So this was one of the technologies that had to be invented in order for the James Webb Space Telescope to happen. This is a plot of diameter of the mirror of a telescope versus year, going back to Galileo's telescope. And one thing you can see here, hopefully you'll agree, it looks like these data points are going up to the right. So astronomers always want bigger and bigger and bigger telescopes. And it's for the reasons I already explained. They gather more light and they can distinguish more detail. And here are some cartoons of the sizes of mirrors of actual telescopes. And let's try to pick a few, for example. By the way, for scale in the lower left, that's a tennis court. And in the lower right is a basketball court. Let's take a look at the Keck telescopes up here, the twin blue telescopes in the sort of center top. And you can see that that's made of segments. You can see some other telescopes that are similar in size, like the Grand Canary Telescope, the Hobby Eberly Telescope, and SALT, South African Large Telescope. But take a look at the Hubble Space Telescope near the tennis court. Do you see it? Look at the size of that mirror. It's tiny. And James Webb is right next to it. Now, James Webb is still tiny compared to some of these big ground-based telescopes. And the reason for that is because it costs a lot to launch things into space. So right now we couldn't launch one of these big ones. By the way, this thing called the 30-meter telescope and the European Extremely Large Telescope and the Giant Magellan Telescope, those three are proposed telescopes. The European one is being built, and the 30-meter telescope and the Giant Magellan Telescope are having funding problems. It turns out the National Science Foundation recently announced that they'll only fund one of those. Those are two American telescopes. They cost about $3 billion each, and NSF doesn't have enough money to fund both of them. If you look carefully, you can see some huge gray circle covering this whole slide. Do you see that? And if you look at the bottom, that was the overwhelmingly large telescope, but it was canceled. That was going to be a 100-meter telescope, and there wasn't enough funding. That became the European Extremely Large Telescope. So JWST is the biggest space telescope, but it's certainly not the biggest telescope. Here are some names of actual telescopes: the Very Large Telescope, Extremely Large Telescope. OWL was the overwhelmingly large telescope, and I think we're running out of words. You can see the oppressively colossal telescope. We have a few more options. There's the final telescope. And in the late 90s, I remember someone published a paper proposing a new telescope, and they called it the Super Huge Interferometric Telescope. But that makes a really bad acronym. And the editors didn't realize that, and they published the paper. And so it was actually presented at a conference. And the whole thing actually was a joke. So we have goofy names for telescopes. Now, where should we put them? On Earth, we like to put them in places where there's not much wind and places that are high, so above water in the atmosphere, dark, away from city lights, and dry, so few cloudy nights. And that means we tend to put telescopes in only a handful of places. Mauna Kea, which is on the big island of Hawaii. If you ever get a chance to visit there, I encourage you to go up to the summit. Chile, the Chilean Andes, which are very dry, and the Canary Islands, which are also volcanic islands, just like the Hawaiian Islands, except they're off the west coast of Africa, and there are some telescopes there. Here's what the atmosphere does to the image of a star. This little animated GIF is probably a few seconds long, and you're looking at one star, and it doesn't look very pretty. It's certainly not a dot. It's blurry, and it jumps all over the place. And that's because the atmosphere is, quote unquote, turbid, is the word that we use. That means the index of refraction varies with time, and that makes stars look blurry. So this is why observing from the ground is not as good as observing from space. It is cheaper, but then the objects are blurred. So instead of observing from the ground, we like to put telescopes in space. That's the Hubble, to get above the blurring effects of the atmosphere. But it's expensive. You can see the Hubble Space Telescope, the size of it compared to a bus. And look at the price tags. The Keck is much bigger than these other telescopes, and it's 100th the cost. So a measly $100 million compared to $10 billion for a space telescope. So you saw the science goals of the James Webb Space Telescope, where we said that we wanted to disentangle the cosmic web, look at exoplanets, explore star formation, etc. All this means that we need a big infrared telescope, but being infrared, we need to cool it to reduce the thermal background of the telescope itself. And what we decided to do was launch it to a location 1 million miles away from the Earth. Take a look at this diagram. The yellow thing is meant to represent the sun, and the blue thing is meant to represent Earth. And these green things are stable points that co-rotate with the Earth. And look at the number 2. See that number 2 position? That's called the Lagrange point number 2. And by placing an object there, it will co-rotate with the Earth instead of trailing. And then we can have constant, consistent communication with it. It turns out that green number 2 dot is 1 million miles away from the Earth, the blue circle. So that's where we launched the James Webb Space Telescope, to this quote unquote L2 location, far from the Earth, so it couldn't be heated by the energy that the Earth radiates. And then there's the solar blocker, which blocks light from the sun. So it's in a nice, cool place. Maybe some of you are familiar with black body radiation. So everything in the universe radiates, emits light. I'm radiating right now. You can't see because my webcam and your eyes can't see infrared light. And it just so happens, because my body is roughly 300 Kelvin, that the peak of my emission's at 10 microns. Your eyes can't see that. And with JWST, we're looking at things in the region of 10 microns or a few microns. And so what we need to do is make sure the telescope and everything around it is cooled so it's not emitting back into itself. And so the James Webb Space Telescope detectors operate at 40 Kelvin. So it's 10 times colder than our bodies. And that means they emit at 10 times longer wavelengths. So instead of 10 microns, they radiate at 100 microns. So what I'm basically saying is we had to cool the telescope and we had to put it far away. Here's one of the dramatizations of why infrared is useful. Here's a picture of the sky on the left in an optical band. So this is what your eyes could see. So you see a bunch of dots. Those are all stars. And then here's a picture I took years ago for my thesis in the infrared. It's the same piece of sky. But on the right, you see 40,000 stars. I know you can't count them now, but I've counted them. So you see 40,000 stars. On the left, you see hundreds or thousands. And the reason for this is because I pointed the telescope at the center of the galaxy, which is obscured by dust, along the line of sight from us to the center, 25,000 light years away. By looking in the infrared, we can peer through the dust. And this is just a property of physics, the physics of light matter interaction. The dust absorbs short wavelengths and it allows long wavelengths to travel through the dust. So basically, you can see here that with infrared, we can see through dust. That's the main point. And here's let me see if I can run this. This is a movie I had the video editing people at Space Telescope make for me, going from your backyard, jumping into a spacecraft, flying into the center of the galaxy with infrared glasses. And at this point, this is a simulation, and I had them sort of rock the point of view like a Star Trek video or something. And those blue stars are young stars around the supermassive black hole at the center of the galaxy. And that's what I was studying at the time I had them make this video. But the main point here is that with the infrared, we can see through the dust to the center of the galaxy. I'm moving along a little bit so I can finish on time. These are pictures of infrared detectors. I was the detector scientist for the James Webb Space Telescope. We had to invent new detectors that would be suitable for the mission. It's one of the things that had to be invented. And here are some of the competitors. On the left is a picture of one of the competitors. That picture I took in my lab. On the right are some detectors made from a different vendor, and there was a competition between two companies, and one company won, Teledyne, and one company lost, Raytheon. And so based on the measurements that I made of the detector performance, NASA chose the Teledyne detectors, and those are now on the James Webb Space Telescope. And here's a picture of one of the detectors, And here's the development team. We're receiving an award from this fellow in the middle, in the back row. He's standing right next to me, and his name is Scott Hubbard. He was the director of NASA Ames Research Center, and we were given the NASA Space Act Award for the development of infrared detectors for space astronomy. Again, we're very happy that these things work because initially they didn't work. So let's move on to some results. I showed you this picture at the end of the movie. This is a picture of a piece of sky containing a cluster of galaxies. It happens to be called Abell 2744. And you can see two regions of the cluster, one on the left and one on the right in the big squares. Now, just about every smudge you can see in these pictures is a galaxy. The big ones have a few 100 billion stars. And we estimate now from these results that there are a few 100 billion galaxies in the universe. So 100 billion is a big number. Billions 10 to the 9, so 1 followed by 9 zeros. 100 billion is 10 to the 11. So there are 10 to the 11 stars in a galaxy and 10 to the 11 galaxies in the universe. So there's 10 to the 22 stars in the universe, each probably surrounded by planets. So if you try to imagine if there's life elsewhere in the universe, there probably is, unless it's extremely improbable. Now, take a look at these inset squares. So one of them is labeled number 1 on the left-hand side of the left big square. And there's another one on the left-hand side of the right big square labeled number 2. And then you can see these insets, number 1, number 2. And in the center of the insets, you can see a red smudge. So those are galaxies that are far away. So they're over to the left on that horn diagram I showed you. And they look red because their light has been redshifted. That is, they emit optical light, but after traveling through the expanding universe, the wavelength gets stretched into the infrared. And this is why the James Webb Space Telescope has to be sensitive in the infrared. To look at faraway galaxies in the early universe, we have to be able to measure the stretched wavelengths of light. And that means the infrared. So these red smudges are galaxies. So these are some of the first galaxies formed after the Big Bang. They're quote unquote only 300 to 400 million years old. And again, I realize that seems like a big number, but again, compared to 13.5 billion years, it's very close to the beginning of the universe. These Z numbers correspond to how far away they are when they emitted the light. And this is a further detail about how we measure those Z numbers. Take a look at the left. There's a image of a bunch of galaxies. Each dot, each smudge is a galaxy. The red ones are in the early universe. And it's kind of a funny shape to the picture, but you can see these tiny little squares and then lines going to the inset picture. And each of these boxes has a red smudge in it. That's a galaxy that's far, far away, as they say, in the early universe. So you can see a Z of 13.2, 12.6, et cetera, et cetera, et cetera. Now, the way this is actually measured is we use the telescope to obtain a spectrum of that red smudge. And on the right, you can see a squiggly line for them, one corresponding to each red smudge. And in this smudge, you can see this red vertical line. That's a spectral feature. We know what it is. And we know that when that light is emitted, it's emitted in the ultraviolet. But we're seeing it in the infrared. I realize you can't see the x-axis. You can't see the wavelength number. But longer wavelengths are to the right, shorter wavelengths to the left. I can see the number barely. It looks like this is around 1.5 microns. So basically, this is a factor of 10 to 15 longer than the wavelength at which the light was emitted by the galaxy. So again, what that means is the galaxy emitted the light in the UV. That light traveled to us over 13.5 billion years. And in the process, it got stretched to longer wavelengths. And now with the James Webb Space Telescope, we see that feature. So we can measure how much it's stretched. and then we know how far away it was, and then we know how old it was, or how long after the Big Bang it formed. That's a little bit technical. I think my kids would say I'm getting too sciencey, but at least you can see there is a measurement that tells us how much the light was stretched, the Z factor. This is another early result from JWST. This is a montage of an X-ray image taken by the Chandra X-ray telescope, overlaid on the James Webb Space Telescope, and it appears that there's a black hole in the early universe. And what's surprising about that is that the black hole is bigger than we thought. We thought it would take a long time to make a big black hole. One of the theories is that a big black hole comes from a small black hole that eats matter over billions of years. But this one already has 100 million solar masses, 100 million times the mass of the sun in a black hole in the early universe. So this is one of the results from the James Webb Space Telescope. Early black holes, and also we're confused that the early galaxies that we're seeing, these galaxies, are bigger than we expected. So galaxies and black holes formed earlier than we had thought. Here's an image of a galaxy cluster. The cluster of um, galaxies in the cluster appear to be sort of yellow, white, and then these striations, these linear features, these are galaxies much further away than the cluster, but the mass of the cluster bends the light from the background galaxies. This is called gravitational lensing. And in fact, we can use gravitational lensing to see this inset. If you look closely, there's this little squiggly red line. This is a single star that's being gravitationally lensed, and it's a single star in the early universe. So again, JWST is a cosmic time machine. We're looking back to the beginning of the universe, and we're able to see stars and galaxies as we planned for it to do. We also use JWST to look at nearby things. These are all nearby galaxies. Nearby meaning tens or hundreds of millions of light years away. And the red is the James Webb Space Telescope data. And what it's showing you is showing you dust in the disk of galaxies, and that's where all the stars formed. So we're seeing this in unprecedented detail. Also, you can see the centers of the galaxies where we think supermassive black holes reside. Mr. Benz, maybe you remember the name of the variable stars that I was studying. They were called Cepheids. I don't know if that rings a bell, but here's JWST results for Cepheids. So it turns out what I was doing in high school was I was measuring the period of the variable star, how many days it took to make one oscillation of light. And that period is related to the intrinsic brightness of the star, and then that could be used to measure the distance to it. If you know the intrinsic brightness of something, and then you look at the brightness of it in the sky, the difference between those two gives you the distance. And this is what Adam Rees is doing with the James Webb Space Telescope. This circle is drawn around a central object. You can see Hubble, there's sort of one pixel where it looks like it's bright, but it was hard for him to know if that was a single star or not. So he used the James Webb Space Telescope. And look at the picture on the left, it's much better. So this is the Cepheid that's the furthest away, 120 million light years. And this sets the cosmic distance ladder, which we use to measure distances further away with other techniques. So we use this to calibrate other techniques. You might know Adam's name. He won the Nobel Prize for discovering in 1998 the acceleration of the universe. So not only is the universe expanding, but the rate is accelerating. And he discovered that. Moving on to the last few results. This is an object that is an exoplanet. And you see all these squiggly lines here. Each of these represents a spectrum separating the light according to wavelength, looking at this planet. And without getting too sciencey, you can see bumps and wiggles for sure. And each of those bumps corresponds to a molecular species in the atmosphere of the planet. And I'll read some of these off because I think it's difficult for you to see. But some are carbon monoxide, so CO, H2O, potassium, so that's atomic, sulfur dioxide, Yeah, that's about it. Water, sodium. So the main point here is we're using the telescope to measure what kind of molecules exist in the atmosphere of this planet. And that's mind blowing considering, like I said, when I was a graduate student, we didn't have exoplanets or we didn't know we had exoplanets. And now we're able to see what their atmospheres are made of. Here's another one. Here it's zoomed in a little bit so you can see some of the labels. This is detecting water. So these are water clouds. So we're detecting clouds in the atmospheres of exoplanets. Okay, I'm going to finish here, and I wanted to generalize this talk a little bit to make the observation that technology is really driving discovery. So with the James Webb Space Telescope, we had to invent a bunch of technology, and that's where the discoveries come from. Here's a related discovery. Maybe you've seen this. That's actually a picture of a black hole, a supermassive black hole, and you can see the donut in the center, and that's what we would expect to see around a black hole. And so this was taken with a telescope that effectively is the size of the Earth. It's called the Event Horizon Telescope. And this comes from technology. This technology happens to be called interferometry. So it was the development of interferometry that led to this discovery. There's another technology, maybe you've heard about it. There's the LIGO, it's called. It's a gravitational observatory that measures gravitational waves. And it turns out that um, when big objects move quickly, they emit gravitational waves that we can detect here on Earth. And each of these circles here represents a star that collapsed into a black hole, or the yellow ones are neutron stars. And then they merged with other black holes or neutron stars. And when that happens, big masses move quickly, and that ripples gravitational waves across the universe. And we figured out how to measure that. And again, this is a triumph of technology. This also uses a kind of interferometry. I'm going to end right there and see if any of you have questions.
Does the James Webb Telescope, you mentioned that it does, it has sensors to be able to measure the atmosphere. Does it also have the sensors for the temperatures above in that atmosphere?
Yeah, yep. So the way to measure temperature is straightforward. It's related to what I said about black body radiation. My body's 300 Kelvin or so. So the peak of emission is at 10 microns. If an object is at 100 Kelvin, then the peak is 30 microns. It's just linear. So all you have to do is measure the light across a broad range of wavelengths and see where it peaks, and then use the black body equation to estimate the temperature of the object.
Now, are there any pictures of the nearest star slash planets where the telescope has zoomed in on that?
No, they're all dots.
Okay.
Like I said before, if you make a telescope bigger and bigger and bigger and bigger, it'll have more and more and more spatial resolution, and we're not there yet.
Thank you.
Yep. Yeah, if you ever see a picture of an exoplanet and you can see clouds and you can see oceans and land, that's an artist's rendition.
Peter, what do you think about the advance of this technology? You have to unmute yourself.
Yeah, mind-boggling is what comes to my mind. It's absolutely amazing.
What has changed since the time when you were doing research in regards to technology and what astronomers used as the main instruments for the research?
Well, it's kind of a broad question. What we're using is still telescopes, but that includes things like the Webb, which are completely out of uh, the realm of what we had when I was a young astronomer. And it's just amazing. Lots of progress. More scientists, more money, more knowledge.
I was having dinner with the head of NASA, Charlie Bolden, about 6 or 7 years ago, and he knew I had worked on the project, and he asked me if it was going to work. But at that time, I was no longer working on the project. So I was able to answer by saying, I no longer work on the project. And that was my answer because it just seemed pretty implausible that the thing would work at all.
It is.
The multi layers in the deployment, it's just mind boggling that would all unfold and unravel without. I mean, the mechanics of that is just staggering unto its own. Not to mention all of the science associated with what you're analyzing and processing, but just the deployment and the unfolding of that, and then the multi layers unfolding is just that's just staggering unto its own.
Yeah, I had two jobs. My one job was detector scientist, and my other job was deployment scientist. I got the two most difficult jobs. um, the other problem with the deployment, which you might not appreciate, is that we didn't have a vacuum cryogenic chamber big enough to test it. So we tested it after launch in space, right? And so that's very risky to do. Um, the other thing is, let's say you did have a chamber and you put the whole thing in a chamber and you pulled a vacuum and it was cryogenic. We couldn't figure out how to turn gravity off on the Earth.
Oh yeah, right.
So you can't test it in zero gravity. Is the problem. And like I said, it worked. But part of that $11 billion cost was risk reduction or testing. We tested the hell out of it. I can tell you a funny story. Recently, someone approached me, and they told me that a rich guy wants to build a telescope like the James Webb Space Telescope. Every now and then, a rich guy comes along who wants to build a telescope, and we always say it's because as a kid he never had a big enough telescope. So we call it an RGT, the rich guy telescope. And so MIT called me to do the detector system for the rich guy's telescope. And his philosophy was opposite of what NASA does. His philosophy was more like what Elon Musk does. You build something, do your best, you launch it, it explodes, they build another one. And because you're doing this quickly, it doesn't cost very much. So the rich guy wants to build a James Webb Space Telescope in 2 years instead of 20 years. And he wants to spend $1 billion. And then he said he'll blow up a few until we perfect it. And a few $1 billion here and there doesn't amount to much anyway, compared to 11 billion. And this rapid prototyping is the approach he's going to take. And it's what Elon Musk does, right? Now, initially, they wouldn't tell me who the rich guy was, but they finally told me it is Eric Schmidt, who is the CEO of a company called Google. And it turns out he has a bunch of billions of dollars. In the end, I don't know if that project is going to happen, but I did put together a proposal for it for the detector systems.
That's staggering.
Well, Don, you had mentioned that some of the telescopes like link like the Keck telescopes. There's two of them, and they link. They link their data together, I guess. To
That didn't work.
Oh, okay.
It's so yes, we pitched that to the Keck family. Yes, we got them to build two telescopes. Yes, when we got the funding to build the first telescope, we put a place for the second one without having the funding. And then we said, let's build another one. And then we tried to connect them and it didn't work. So now we have two telescopes that point at different things.
Okay.
Still not bad. Now, the Europeans did better. You remember I said that there's something called the Very Large Telescope? That's kind of a misnomer because it's actually four telescopes in Chile. And each telescope is 8 meters in size. So they've successfully combined the light of all four. So we failed, they succeeded. Now, in the radio regime, it's much easier because the wavelengths are much longer. So if your path lengths are in error, that's a smaller fraction of a wave. And so for radio telescopes, it's common to combine the signal from multiple telescopes. In fact, you saw it in the movie Contact when Jodie Foster was using the Very Large Array, the VLA. That's 27 radio telescopes in New Mexico that are meant to all point at the same thing at the same time and have their data collected. And the resolving power of that array is equal to the resolving power of one telescope with a mirror the size equal to the furthest distance between the telescopes. You see what I mean? So
Yeah.
instead of building a telescope this big, build a bunch of small ones and separate them. Now, you don't have the light gathering power as you would have if you had a single huge dish, because there are going to be huge gaps between the telescopes, but you'll have the spatial resolution. And that's why the VLA was built.
You have the same kind of atmospheric issue with distortion with the radio telescopes as you do with the light gathering telescope?
No, only because think of the distortion as inducing or injecting an error in the propagating wave, and think of it as inducing an error of a certain size. Okay, that size compared to optical wavelengths is massive. This size compared to radio wavelengths is small. So the fractional error is nil in the radio. So the radio is impervious to atmospheric turbulence. That's why no one would ever propose launching a radio telescope. It's just fine down here.
Okay.
Now people do propose to launch a radio telescope on the moon, and so some of us are thinking about that, putting down a huge telescope on the far side of the moon, the piece of the moon that never points towards us. And then we use the moon as a big blocker of Earth's radio transmissions that we're spewing out into space. So we can block our own radio pollution by building a telescope on the far side of the moon.
Hey, I just thought it might be interesting to contrast all the fantastic technologies we have nowadays with some of the earliest attempts at finding exoplanets. I remember when I was in high school, roughly 60 years ago, I lived near Swarthmore, Pennsylvania, which had where Swarthmore College is, and they had a very nice telescope installation there. And the head astronomer there was working on trying to detect exoplanets by carefully photographing nearby stars over a period of many years to detect a slight wobble in the star. So if there was a heavy planet going around the star, the planet did not just circle the star exactly, but they both circled the center of mass that was somewhere between the star and the planet, and
The Berry Center.
usually inside the star or right, just slightly outside of it. But that caused this, as the planet went around it, the star would wobble a tiny little bit in a corresponding circle. And he was actually getting very close to detecting those wobbles in some of the nearby stars. But it was so difficult, and it took years to do it, that very few astronomers were working on things like that back then. And he thought he had actually pretty much detected at one star that he thought there might be a large planet going around it. But that was the best they could do. There was no other information about, the atmosphere of the planet or anything, just the fact that it existed. And that's the best we could do at that time.
Yep. Yep. I was around eating lunch with those guys at the cafeteria of the telescope. And what they were doing is, the way you explained it is, it was spatial, watching the wobble. The way they were doing it is measuring the velocity of the star as it goes around the Berry Center. And you can measure the velocity by looking at lines in the spectrum that keep shifting back and forth due to Doppler shift
Yes.
as the star goes. Yeah. So they were at 50 meters per second they could detect. And now we're below a meter per second. So like a factor of 100 better. And there are people who are trying to get down to tens of centimeters
Wow.
per second. So, the further you can go down, the smaller the mass of the planet you can detect, because smaller and smaller and smaller planets make smaller and smaller wobbles. And by the way, just for reference, if the solar system just had the sun and Jupiter, then the common center of mass would be right at the surface of the sun. So not quite in it, not quite out of it.
Yeah.
So, Don, what are you working on currently?
You know what? I stopped shy of showing you something. So let me just show you just the picture at least, because that's the answer to your question. Can you see that?
Yeah.
Yes.
Okay, so this is the Habitable Worlds Observatory. So this is a good follow-up to our conversation that we just had. So imagine you find planets. Imagine you measure the composition of their atmospheres. Then you want to look only at the ones that are at a Goldilocks distance from their stars, such that they would have the right temperature for liquid water. And we call that habitable. If the temperature is between the freezing and boiling point of water, then we say that planet might have life. It's habitable. And so now NASA called me 2 weeks ago and asked me to develop the detectors for the Habitable Worlds Observatory. So I now have deja vu all over again. It's like 1999, and we're going to say it's going to launch on a certain date for a certain amount of money, and it'll do neither. So now I'm at the point of being one of the developers for the detectors for this thing that we intend to detect life on habitable worlds by measuring the presence of biosignatures in their spectra, things like water and oxygen and methane. If you see all those things together, we think that means life. And if you look at the picture of the cartoon, I think what someone did was, I think we just gave an artist a picture of JWST and we just said, make it better, make it bigger. And they drew this picture. So that's what I'm doing.
Exciting.
It's remarkable.
All from your science seminar class, Mr. Benz.
Oh,
Look what you did.
that was just a dot in the sky. Yeah.
So when you're having breakfast with your children, do you occasionally delve into a scientific monologue about the remarkable world that we live in, with molecules swimming around in the world around us as they're eating their cereal? And then
Yeah. We talk about that.
that too
Yeah,
sciencey.
yeah, yeah. We talk about stuff like that. I try to sort of pepper our conversations with things that are happening. Um, and depending on their age, they're more or less receptive. I found that when they were younger, like below 10, I could easily go on hours long walks with them, and we could look at the trees and the birds and the sky and the moon, and we could talk about how things work, um, which is which is what Feynman used to do. He described doing that with his kids in his book, uh, describing what all the animals are doing and whatnot. As they get older, they want to post pictures on Instagram. That seems to be their main interest. Uh, they don't listen as much. Also, it becomes a little bit of background noise. So when I say, you know, I'm working with Adam Rees, he won the Nobel Prize in 2011. By the way, he threw my bachelor party, which he did. Or I say John Mather asked me to work with him on a new project. John Mather won the Nobel Prize for measuring the cosmic microwave background. Or Brian Schmidt. I just joined a project with Brian Schmidt. He won the Nobel Prize. Did a project with Saul Perlmutter. He won a Nobel Prize. Andrea Ghez and Reinhard Genzel have won Nobel Prizes. I've worked with them, and I'm co-authors with them on some of the Nobel Prize work. Uh, for my kids, it seems to not be extraordinary. It seems to be Dad talking about the factory. He went to the factory
Right.
that day, and he shoveled some coal, and that's fine. I introduced them to an astronaut, Don Pettit, who is the photographer geek of the space station. He's the guy who yells at the other astronauts because they didn't take enough pictures. Okay, he's been on the space station for 400 days, and he came here and asked me to do a project with him to remove the cosmic ray damage from his images that he took on the space station. And I introduced him to my kids, and I said to my one kid, I said, golly, he's a hero. That guy's a hero, an astronaut. Astronauts are heroes. And I said, his kids must see him as a hero. And my one kid said, she must have been maybe 7 or 8 years old. She said, no, kids that grow up in a certain family just see their parents as regular people. So I don't think that their kids know anything about him being a hero, which is kind of funny. But they renormalize everything that's around them.
Well, I can't help but think, first of all, you've had a incredible career. There's no doubt about that. But what a marvelous testament you are to the public school system, and also to how one devoted, dedicated, enthusiastic teacher can be instrumental in affecting the life of an individual that can go on to do great things.
Yep. Yeah. It's I try to tell my students and my kids also that if you focus on one thing and you get lucky enough or arrange to have the right people in your life, you can go farther than anyone else has ever gone. Not that I'm saying do that, because that's a pretty linear life that might be less interesting than meandering around, but you certainly can do it.
Yeah, it's really quite remarkable. Any other questions, Uwe? Rich, you got any closing thoughts or comments?
No, it's just amazing to watch, and I'm so happy that Dr. Don said that he would give this talk, and of course, is so very proud. We're going to take this recording, we'll put it on our YouTube channel, and if anybody's interested in seeing that, you could probably do a search for it. But if you write to either of us, we can certainly give you the links. I have, I don't know if I can share this. This is the email address that we've created. So if you had any questions about how to find the YouTubes or any of the links, that type of thing, or if you want to give a talk on ecophilia, please. We're always looking for more people to do that. So I just put this on the screen so that people would know where to write to. Again, Don, thank you very much. That was amazing, and I'm going to be sharing this link with lots of folks.
Thank you very much, and thank you for all you've done, Mr. Benz, and thank you for all the people who've joined. It's been a pleasure of mine.
Hey, Rick,
Thanks, Don.
question on the email address.
Yes.
It says Ecophilia, Ohio. Do you have aspirations to go global?
No, it's just that ecophilia was taken, so I added the Ohio. I could have put Cleveland, I suppose, but
Today, Ohio, tomorrow, the world.
there you go, exactly. And then the universe. What the heck?
Thank you.
Yeah, we had a question on the chat about the rest of the programs. We do have Judy Samrick scheduled in November for a vernal pool presentation. Next month, we have a talk on the Great Lakes, the shipwrecks of the Great Lakes. It should be quite fascinating. We're still populating the schedule for the rest of the year, but more detail on that to come. I will be having a meeting next month with Darren Croft and a graduate student who's interested in becoming involved and kind of curating ecophilia, perhaps within the auspices of Case Western Reserve University. And so I think that's all the news to share as far as the updates. Again, Don, thank you very much. Peter, thanks for continuing to be a motivator. Peter, you got anything to add, or are you ready to sign off?
Well, ready to sign off. Thanks everyone for joining. It's always so wonderful to hear and listen and watch and learn.
Absolutely. And until we meet again, folks, take care of yourself, okay?
Thank you very much. Thanks, Don.
Yep, bye.
Don.
Good.